Hello everybody, welcome to another video where today we are doing the 2021 AQA GCSE Physics Paper 1, and without any further ado, let's jump straight in. Question 1. Figure 1 shows an electric car being recharged, and we're just given a small little image of it. The charging station applies a direct potential difference across the battery of the car. What does direct potential difference mean? Well, that simply means that the polarity of the supply does not change like it would do with alternating current. For 1.2, which equation links energy transferred, power, and time? And that is that energy transferred equals power times time, more often given as just power equals energy transferred over time. Question 1.3, the battery in the electric car can store 162 million joules of energy. The charging station has a power output of 7,200 watts. Calculate the time taken to fully recharge the battery from zero. So what we simply do is we plug the numbers into the equation and then just rearrange for t, getting an answer of 22,500 seconds. Then for 1.4, it's another equation one, which equation links current, potential difference, and resistance. And that is that V equals IR. And then for question 1.5, the potential difference across the battery is 480 volts. There is a current of 15 amps in the circuit connecting the battery to the motor of the electric car, and we have to calculate the resistance of the motor. Once again, we plug voltage in, plug current in, just plug it into the formula, rearrange for R, and we get an answer of 32 ohms. Then for 1.6, different charging systems use different electrical currents. How does the time taken to charge a battery using charging system A compare with the time taken using charging system B, where A has a current of 13 amps and B has a current of 26 amps, and they both have a voltage of 230. Well, this one's actually rather, I say complicated if you want to do it mathematically. The options are half, the same, or double. It's doubled. To do it mathematically, power equals current times voltage. Double the current with the same voltage means double the power. Double the power means half the time taken. Of course, you could just see, oh yeah, obviously more current means it takes less, more current means it takes half time, so half the current means it will take double the amount of time. But yeah. Question 2. Energy is released from the sun by nuclear fusion, and we just have to complete the sentences. Nuclear fusion is the joining together of nuclei. During nuclear fusion, the total mass of the particles decreases, and this is because the sum of the mass is converted into energy using the very well-known formula E equals mc squared, which we do not have to use here. Nuclear fusion of deuterium is difficult to achieve on Earth because of the high temperature needed. Electricity is used to increase the temperature of 4 grams of deuterium by 50 million degrees Celsius, and the specific heat capacity of deuterium is 5,200 joules per kilogram Celsius. Calculate the energy needed to increase the temperature of the deuterium. We simply use the formula from the equation sheet, E equals mc delta theta. I just use T because my keyboard doesn't have theta for change in temperature. And yeah, you simply plug it in. Converting grams to kilograms by dividing it by 1,000, plug in 50 million, plug in 5,200, and you get an answer of 1,040 million joules. Next up, 2.3, the idea of obtaining power from nuclear fusion was investigated using models. The models were tested before starting to build the first commercial nuclear fusion power station. Suggest 2 reasons why models were tested, and is to A, make sure the fusion process is possible, and B, to assess safety risks. And then generating electricity using nuclear fusion will have fewer environmental effects than generating electricity using a fossil fuel. Explain one environmental effect of generating electricity using fossil fuels. Well, it releases carbon dioxide, which causes global warming. There's many you can go for, but that's just the simplest one. Then for question 3, student A investigated how the current in resistor R at constant temperature varied with the potential difference across the resistor. Student A recorded both positive and negative values of current, with figure 2 showing the circuit student A used. And this is just a circuit. we have to describe a method that student A could use for the investigation. Well, we have to set up the circuit with the resistor, an ammeter in series and a voltmeter connected in parallel, as always, across the resistor, and you have to include a variable resistor or variable power supply to control the current. Don't know why it says variable power supply when we're just using resistor. Keeping the current low prevents the resistor from overheating. You have to measure and record the current from the ammeter and the potential difference across the resistor from the voltmeter. And then you vary the resistance of the variable resistor to obtain new readings. And then we just have to making sure to switch the current off between the adjustments of the variable resistor to avoid unnecessary heating. Then you reverse the connections to the power supply. So we just flip the power supply around. When we can do that because there's no diode components or LED components. And so we do that so the current flows in the opposite direction, and we repeat the measurements again to obtain negative values. So we can, and then with all those different values, don't think it's actually the answer. Yeah, we don't actually have to do it. We should get a straight line graph because a resistor is an ohmic conductor. And then the resistance is simply 1 over the gradient of a current voltage graph, but that's not required for the actual question. Oh, it says plot a graph of current against resistance. That's meant to be current against voltage. Plot a graph of current against... When did I messing up completely? Yes, that's meant to be current against voltage. So you plot a graph of current against voltage for all the different things, and then you should realize it's an ohmic conductor. Then for 3.2, student B repeated the investigation. During student B's investigation, the temperature of resistor R increased. Explain how the increased temperature of resistance R would have affected student B's result, and that is that current and potential difference would not be directly proportional as the resistance would increase. And then for figure 3 shows the scale on a moving coil ammeter at one time in the investigation, and we're asked what the resolution is. Now the resolution is the smallest possible reading, so it's 0.2 amps because like the smallest possible precision it can have is 0.2 amps. Then student B replaced the moving coil ammeter with a digital ammeter. Figure 4 shows the reading on the digital ammeter. The digital ammeter has a higher resolution than the moving coil one. Give one other reason why it would be better to use the digital ammeter throughout this investigation, and that's because it has less chance of you misreading. Like you're less likely to misread this than you are to misread this, and that could be for a number of reasons, such as like parallax error and stuff like that. Then question 4, a student investigated the density of different fruits. Table 1 shows the results. The student determined the volume of each fruit using a displacement can and measuring cylinder, and what other piece of equipment would the student need to determine the density? Well, density equals mass over volume. You can use the displacement can and measuring cylinder to work out the volume, so you only need to find out the mass, and you can do that using balance scales. And then, as I said earlier, density equals mass over volume. For the next question, you simply just plug those numbers in and rearrange for V to get a volume of 125. So much, if you've watched any of my other videos, if you know how to rearrange, you can pass GCSE Physics just knowing how to rearrange equations and using your formula booklet. I do believe it's a bit of a joke in that regard, but yeah, you rearranging just makes GCSE Physics so much easier if you know how to do it. 4.4. The student only measured the volume of each fruit once. The volume measurements can not be used to show that the method to measure volume gives precise readings, and to give the reason why is because you need repeat readings taken to show that the readings are close together. The readings could be accurate, because like it could be close to the true answer, but they can't really be precise as you only have one reading. And for precise readings, the readings need to be close together. There's a diagram on that. Yeah, now I said there's a diagram on it, I have to put it on screen, don't I? That's great. Great job for me. bothering future me. Then anyway, 5.1, during 1 year, 1.25 times 10 to the 18 joules of energy was transferred into the national grid. The number of seconds in 1 year is 3.16 times 10 to the 7, and we have to calculate the mean energy transferred from the national grid each second. Well, the mean energy transferred from the national grid each second is the same as power. Power equals energy over time. Plug the numbers in. Energy divided by the time in seconds, and that is 3.96 times 10 to the power of 10 joules, which is the amount of energy each second. And then we're just showing a house with solar panels on it. When the electricity generated by the solar cells is not needed, the energy is stored in a large battery. Nowadays, I'm saying nowadays, this was only like 5 years ago, what happens most often is that it just gets put into the national grid, and then you get a small rebate from the government or from the energy company. The charge flow through the cables between the solar cells and the battery in 24 hours was 27,000 coulombs, and we have to calculate the mean current in the cable. Firstly, we convert 24 hours into seconds by multiplying it by 3,600, or just multiplying by 60 twice. Then we use the formula from the formula book, charge equals current times time, rearrange to get current, and we get current being at 0.3125 amps. It's another simple rearranging question. The total power input is 7.8 kilowatts or 7,800 watts. The efficiency was 0.15. Just plug it in and rearrange. I didn't even do the rearranging just because, like, I know the formula's in the formula book. The answer is 1,170 watts. It is unlikely that all of the electricity that the UK needs can be generated by solar power systems. Explain why. That's because a really large area of land would be needed to cover with solar cells due to the low useful power output of solar cells, because like it only has an efficiency of 0.15. You have to cover a lot of area. Then for question 6, we're showing the mass numbers and atomic numbers for the nuclei of 5 different atoms. How many neutrons are there in a nucleus of atom A? Well, it has a mass number of 226 and an atomic number of 88. The mass number is the amount of neutrons plus the amount of protons, and the atomic number is the amount of protons. Just realized that's atom B. 234 to 86. It's just 234 minus 86 to get you an answer of 148. Which two atoms in figure 6 are the same element? And that is atoms... Oh my goodness, I got it wrong. I've never actually gotten something wrong in one of these videos before. It's D and E, because D and E share the same atomic number, which means they have the same amount of protons, which means they are the same atom. Then nucleus B decays by emitting an alpha particle. Draw an arrow on figure 7 to represent the alpha decay. Just goes from, loses 2 atomic numbers and 4 atomic mass, and it's just, that's the new atom here. It only asked me to draw an arrow, not the actual atom. And what is meant by the random nature of radioactive decay? It means you can't predict when a particular nucleus will decay. A polonium nucleus decays by emitting an alpha particle and forming a lead nucleus. The lead nucleus then decays by emitting a beta particle and forms a bismuth nucleus. The bismuth nucleus then decays by emitting a beta particle and forms a polonium nucleus. Explain how these 3 decays would result in the nucleus of the original element. Well, that's because 1 alpha decay would decrease the proton number by 2, and then 2 beta decays would increase the proton number, also increase the proton number by 2. So the number of the final nucleus is the same as the atomic number of the original nucleus. And I'm just gonna quickly take a photo of this and send it to my friend to annoy them. Anyways, next question. Question 7. A student investigated how the current in a series circuit varied with the resistance of a variable resistor. Figure 8 shows the circuit used, and figure 9 shows the results, and I've just done that there. The battery had a power output of 230 milliwatts when the resistance of the variable resistor was 36 watts, and we have to determine the potential difference across the battery. Well, get the current using the graph and the resistance, and to work out the potential difference, we simply use the formula P equals IB, plug in the power, convert it into proper watts, use the current you got from the graph, and just rearrange for voltage, and you get a voltage of 2.875 volts. The student concluded that the current in the circuit was inversely proportional to the resistance of the variable resistor. Explain how figure 9 shows the student is correct. Well, if you're any good at maths, you'll know that things being inversely proportional means that in this case, the current would be equal to K over the resistor, or more commonly, how it works in physics, K, the resistance, times the current is always equal to K. And what I've done here is I've just done it for a couple of the points. It's always equal to 2.88. You probably actually want to put the calculations. Okay, you can't take the calculations across the page. You probably want to put the calculations here. It's the fact that the product of current and resistance always equals a constant, or in this case, 2.88. Alright, next question. Figure 10 shows a circuit with a student connected incorrectly. Explain how closing the switch would affect the current in the variable resistor. Well, the current would be almost zero in the variable resistor because the switch has effectively zero resistance. So all the current will flow around that way instead of this way. Art. Then for question 8, figure 11 shows a toy car in different positions on a racing track. The toy car and racing track can be modelled as a closed system. Why can the toy car and the racing track be considered a closed system? Well, it's the fact that the total energy of the racing track and the car is constant. And then the car is released from rest at position A and accelerates due to gravity down the track to position B. We're given the mass of the toy car, the vertical height between position A and B, and the gravitational field strength. Now, first thing I did is just convert this to meters, so 0.9 meters. Then this question actually annoys me a bit, because AQA always annoys me. The mass of the toy car doesn't matter. They've had questions before about how the mass of this stuff doesn't actually matter. That's because the energy it gains in kinetic energy is equal to the energy it loses in gravitational potential energy. So you set gravitational potential energy equal to kinetic energy, and the m's cancel out. This mass could be 1,000,000 kilograms, and it wouldn't matter. I was going to say it could be 0. You can't divide by mass if mass equals 0, because you can't divide by 0. But yeah, you just rearrange it. You just cancel out the masses. 0.5 times v squared equals gh. 0.5 equals 2 times 0.9 times 9.8, and then you get a final answer of v equals 4.2. I'm very disappointed in how common of a question it is. Why does the mass not matter? That they give you the mass because it's unnecessary. Next question. Figure 11 is repeated below. At position C, the car's gravitational potential energy is 0.2 joules greater than at position B. How much kinetic energy does the car need at position B to complete the loop of the track? And the answer is that it is more than 0.2 joules because the car needs to be moving at the top of the loop. Okay, now moving on to question 9. A teacher demonstrated the relationship between the pressure in a gas and the volume of the gas using a pressure gauge, a syringe, and a plunger. This is the method used. You record the initial volume of gas in the syringe and the pressure reading before any weights are attached. Add a 2 Newton weight to the syringe. Record the volume of the gas and the reading on the pressure gauge. Repeat steps 2 and 3 until a weight of 12 newtons is attached to a string. What was the range of force used? And that is from 0 newtons to 12 newtons, because it starts off with 0 rate on it. And what is one control variable in this investigation? It is the temperature of the gas. When the volume of the gas in the syringe was 45 centimeters cubed. The pressure gauge showed a value of 60 kilopascals. Calculate the pressure in the gas when the volume of gas in the syringe was 40 centimeters cubed, and it also wants it in kilopascals. Well, pressure times volume equals a constant. And as I did earlier on in this test, if two things are equal to a constant, you can just set them equal to each other and do the maths directly. So 45 times 60 equals 40 times the volume. Rearrange for the pressure and you get a pressure of 67.5 kilopascals. I don't know why I was so sloppy while doing this test. I still would have gotten all the marks. When the volume of gas in the syringe increased, the pressure on the inside walls of the syringe decreased, and we have to explain why. And that's because there are less frequent collisions between the particles and the walls to the syringe, causing a lower average force on the walls of the syringe, and pressure is the total force per unit area, and the area is constant, so if the force decreases and the area stays the same, the overall pressure decreases. Then figure 13 shows some overhead power cables in the national grid. Explain the advantage of transmitting electricity at a very high potential difference. A very high potential difference means very low currents, which means less thermal energy is transferred to the surroundings, which increases the efficiency of power transmission. It is dangerous for a person to fly a kite near an overhead power cable. Figure 14 shows a person flying a kite. The person could receive a fatal electric shock if the kite was very close to but not touching the power cable, and we have to explain why. Well, that's because the electric field strength is very high, causing the air to become ionized. And then the air being ionized means it can conduct a charge, which means then the kite conducts the charge to the person. A scientist investigated how the potential difference needed for air to conduct charge varies with the distance between the cable and the earth. The data in figure 15 gives the relationship between potential difference and distance when the air is dry. When the humidity of the air increases, the air becomes a better conductor of electricity, and we have to draw a line on figure 15 to show how the potential difference changes with distance if the humidity of the air increases. And what it is, the line just has to be like underneath this line of the potential difference needed. I said it could conduct a bit further. That doesn't actually matter as long as all of this line has lower values than this line. Because obviously less potential difference is needed if it's a better conductor. Figure 16 shows a cross section through a power cable. A 1 meter length of a single aluminum wire is a better conductor than a 1 meter length of the steel wire. The individual wires behave as if they were resistors connected in parallel. Explain why the current in the steel wire is different to the current in a single aluminium wire. The potential difference across the wires, or like the cable, is the same, but the resistance of the steel wire is greater, and so there is less current in steel. The student investigated how the temperature of a lump of ice varied as the ice was heated. The student recorded the investigation until the ice melted and then the water produced boiled. Figure 17 shows the student results. The power output of the heater was constant. The specific heat capacity for ice is less than the specific heat capacity of water. Explain how figure 17 show this. Well, the gradient for ice is steeper than the gradient for liquid, which means that less energy is needed to increase the temperature by a fixed amount, aka the specific heat capacity is less. For 11.2, the specific latent heat of fusion of ice is less than the specific latent heat of vaporization of water. Explain how figure 17 shows this. Well, water took more time to vaporize than the ice took to melt, which means that less energy is needed to change the state from solids to liquid than from liquid to vapor. A second student did the same investigation and recorded the temperature until the water produced boiled. In the second student's investigation, more thermal energy was transferred to the surroundings. Describe two ways that the results of the experiment in figure 17 would have been different. Ice would have taken more time to increase in temperature, and the ice would have taken more time to change the state. When the water was boiling, 0.03 kilograms of water turned into steam. The energy transferred to the water was 69 kilojoules. Calculate the specific latency to vaporization of water. And we're ending off with a rather easy one. Just get the formula from the formula booklet. E equals mass times latency to vaporization. Rearrange, and you get a latency to vaporization. I need to count the zeros. 2,300,000. And for the units, well, because you're dividing energy by mass, it's going to be joules per kilogram. Or you could have done it in kilojoules per kilogram if you just divided by 1,000, and then you get 2,300 kilojoules per kilogram. Or you could have done it in joules per gram, joules per megajoules per kilogram. Any unit, as long as your maths makes sense. Anyway, I think that's the end of the paper. If you've enjoyed it, make sure to like and subscribe, and I'll see you next time for another past paper video.